All right, welcome. It's Friday. We're almost finished with 1 week of online classes. Lots of updates, lots of changes going on. I know some of you are already talking about it. The new information that has been released by the College Board. The tests are not canceled. They're not canceled. We're still going to do the test. It's going to be online. Take home AP test. Can we get a 100% pass rate in chat, please? Can we get 100%? There it is. Let's go for that 100%. Now, obviously they're going to implement ways so that it's all personalized, and I'm sure they'll have force you to use some sort of app to take this test. But essentially, it's supposed to be a smaller test, so it's not going to be 4 hours long as usual. It'll be a smaller version of the test. But they're also cutting out some of the topics. However, for us, we're almost done, so none of that really matters to us. We're actually almost done with the curriculum. We have combination, Kirchhoff's loop rules, and then from then on, what we would have done is we would have done a lot more practice. It's this class is not just about passing the AP test. That's a minor goal, a minor achievement. This program is designed so that you can, after finishing this, you can go to any university and just be basically top of your class. You will know everything you need to actually major in this stuff. What do you think about at-home AP tests? Well, I don't know enough details of what kind of app they're going to use, but it is what it is. I will say this: if you want a star on my wall, you're going to have to get a 5 in both this take-home test as well as my actual final that we take. My final is going to cover everything because we learned everything. So for your star, you're going to have to do both. That's what I think of the take-home test, if you know what I mean. So in any case, we will finish off combination circuits. This is stuff that you'll definitely need when you take AP Physics C next year. And so, what if we don't go back to school? Well, I'm going to give each and every one of you, I'm going to make 60 different finals and give you your final, and then time lock it so you have a certain amount of time to finish that question, or something or rather. Hopefully I don't have to do that, because that's a lot of work. What about FRQs then? Okay, stop asking me questions about that stuff, because I can't give you those answers right now. What you as a student need to do currently is prepare for all the stuff we've learned as if nothing has changed, based on what we've learned, what we've covered. Of course, I am cutting some stuff out from what I've taught last year, just because of the circumstances, but basically whatever I am covering, you are responsible for, and you potentially could be tested on any of that material. Okay. What about effort? Well, online test doesn't mean multiple choice. It means that you are making a submission that is online, so it could be anything, right? I could have you write really quickly and then take a picture and upload it within so and so. But until College Board gives us the actual type of software they're going to use or whatever it is, I don't have the information of how you're going to actually submit all of that stuff. All right, and so let's go and prepare. We want to talk about combination circuits today, which means we're going to combine both series and parallel elements. And to, I guess, make you feel slightly better when you prepare for the AP test, which is after all of this stuff. We're going to focus from remember, we only go up to Unit 8, but our Unit 8 combines a bunch of other things in the College Board. College Board has 10 units, we have 8. For us, in our version, we're going, the AP test would be 1 through 7.5, meaning all the way up to simple harmonic motion, is potentially up for testing on the AP test. So we'll focus more on Unit 1 through 7 during our review process, less on Unit 8 in electrostatics and circuits. All right. We looked at parallel circuits yesterday when we saw that by making more pathways, we start to drop the total resistance in the system. Okay. Total resistance in the system. Every time we open a new branch, the more current can flow through the new branch. Typically in your house, all of your outlets that you have are all parallel. So essentially they're kind of open like this, meaning the plugs are just open parts. And when you plug something in, what you're doing is you're completing one of the chains. And I don't want you to see these circuits in any kind of sequential order, in that this resistor here on the left is not first, and this one is not second. There is no first and second or third. Everything happens all at once. There is no sequence to this. Although when we're analyzing circuits, sometimes I might say this resistor first or this resistor second, but in reality there is no first, second, or third. Okay? All of it gets the power at once, essentially. So you can plug something in over here and leave the other ones blank, and this will still send current through all 4 of these pathways that are connected. Okay. All right, so when you plug something in, you're completing a new pathway, a new bridge. This is going to decrease the overall resistance in your home, which means that you're going to draw more and more current. Okay? It could get to the point where you have your computer on, your hair dryer on, you're blasting your boombox, wherever that is, and you're trying to charge your laptop, etc., etc. When you use too much, okay, too much current means the wires will eventually dissipate some of that energy, will heat up, and potentially cause a fire. And to save ourselves from burning our house down, we put something called a fuse or a circuit breaker right in the front. F. Oh no. Okay. There we go. F. Alright, so let's go to the PowerPoint view. Alright, we know that open and closed circuits based on your switches. When the switch above schematic, well, the schematic is the standard circuit with a battery, switch, resistor. Are circuit breakers the same as fuses? So we're going to talk about that right now. Good question. So a short circuit is a dangerous situation where the load has accidentally been bypassed. Current is very large and causes wires to get hot. So either plugging in a bunch of stuff pulls in a lot of current, or if you create a short circuit in your system, that also causes tons of current to flow through. And when that happens, you might cause a fire. So we put fuses or circuit breakers in the circuit to save ourselves. All right. So what are they? Okay. A fuse is kind of a miniature version, typically in circuit boards. So if you look at like a motherboard or any kind of circuit board, you might see a capital F, and there's a little rectangle next to it. That is a micro fuse. There's also one that is slightly bigger than that. It looks like a cylinder, a small cylinder, about a centimeter in size. There's like a metal contact part on the 2 sides. Okay, and inside is basically a see-through glass or some sort of plastic, and you can see a little thin little wire in there. So this is slightly bigger than those micro ones that you have in an actual circuit board, but it functions the same way in that a fuse is a one-time use only. So when I put this in here, the fuse is able to allow current to pass through it normally. Normally it acts like a wire. Acts like a wire. Oops. Okay, up to a certain amount of current. So up to threshold. Okay, so some fuses will say, I don't know, like 4 amps. This means as long as the current is less than 4 amps, then you're okay. It just acts like a wire. Your system's going to work. However, as soon as you drop more than 4 amps, the fuse will blow, which means that this wire, this thin little wire that's inside, will heat up so much that that it melts and breaks. And now you have a hole, and the hole stops the current from flowing. So when this breaks, the current can't pass through this hole, so it turns the entire thing off. So when I total, or I should just say I, it depends on where you put the fuse, I is greater than the threshold, the value it can withstand, fuse will melt. Oh, so the fuse will melt and break the circuit. All right. So a fuse is a one-time use only in that once this metal thing melts and breaks, there's no way to replace it. So these are kind of like heroes. They're giving their lives away so that everything else in your system does not get all of that current, does not melt, and so your computer and your phone and all that stuff is safe. This fuse will give its life away. But in homes, we don't really use fuses. Fuses would be, kind of small. Certain devices actually have fuses inside, right? A circuit breaker is a larger version of a fuse. Okay, but multiple uses. You can use it over and over again. Up to a certain point, of course. Okay, what is a circuit breaker? Well, similar to a fuse, fuse is a very thin little metal. A circuit breaker is actually larger. So imagine a rectangular piece of metal. Okay, so if you had a circuit, here's your battery, and you have a rectangular piece of metal that connects the bridge of everything else. Okay, so this is your circuit breaker. What is it doing? Well, similar to the fuse. No, it gets so hot that it melts because it's very thin. Circuit breakers, all metals technically, all metals expand. So this is a chemistry thing. If you want to learn more, consider taking AP chemistry. I'm sure they'll teach you all of this stuff. Metals expand. Okay, ask I don't know, Saka or Lin. Metals expand when they get hot. All right. So as more and more current goes through the circuit breaker, this metal chunk will get hotter and hotter, and as it does that, it gets too big. Remember this area here, this portion where you have the circuit breaker has a limited size, in that once the circuit breaker gets hot and it gets bigger, it can't fit in there. Therefore, it pops out. So now it looks something like this. It's too long to fit in there, so it pops out. And when it pops out, the connector is open. Open means the system is off, and now you have no power. So in your homes, you have circuit breakers somewhere in your house. Look along the walls there. there's this little cabinet, little door or something that you can open, and once you open it, you'll see a bunch of sliders. Okay, a bunch of sliders like this. It's in someone's room. If it's not in your room, or it's probably in your parents' room or whatever it is. But there's a bunch of sliders, and it's a little slider thing. Okay, these are all the circuit breakers, and you'll see that they are labeled. So one of them might say like living room, one of them might say garage, or I don't know, kitchen, okay, etc. And so each pathway, each pathway has its own circuit breaker that controls those rooms. Okay, so if your room is pulling too much current, you might heat up your circuit breaker so that it's too large now to fit in your circuit. It pops out. Now your system is open, therefore no current can go can flow through. Okay, this is when nothing works in your room. So what do you do? Well, don't rush to this cabinet to slide it in again. So when you're sliding it in, you're actually kind of like the flashlight. You're actually pushing the circuit breaker back into the circuit so that it looks like this, where it's nice and connected. Now, when it's too hot, it's still kind of big. Therefore, if you try to put it back in immediately, it might not work. Typically, you want to wait like 5 minutes or so. Wait 5 to 10 minutes. This would be good to go. It'll cool down. It'll come back down to its original size, and then you can easily slide it in and push it back in, so that you can restore power in your house. Okay, so wait a few minutes, let it cool down. Don't try to rush and try to get the power back. If you're gaming and you get disconnected, yeah, just chill out and go to the bathroom or something, and then you can go turn it back on. All right, Steve Top, what's the difference between a fuse and a circuit breaker? This is your moment to shine. Hey chat, hey Irfan. One is one-time use. Which one, Steve Top? Oh, I mean Stove Top. Good job, Charlene. The fuse is one-time use. So typically you'll see fuses in circuit boards. So your motherboard on your computer has a bunch of those. Any kind of device, really. Your calculators have fuses. Our voltmeters have fuses. So any device pretty much has fuses just to protect itself. And that's from the idea that a short circuit can develop in your system. So let's talk about short circuits. Sure, it's not just about plugging a bunch of stuff in, but this thing can happen. Okay, so imagine having your stuff in parallel, okay, and then all of a sudden some material, did Mr. Z address the, yeah I did, go watch the video. Some material can create a new pathway. So imagine a piece of wire that kind of touches the top end here and the bottom end here, or it could be any other material, as long as it's conductive. So a conductive material can create a new pathway. This is similar to getting a bypass heart surgery, right? Well, why do people get bypass heart surgeries? Well, that's because the plumbing gets clogged up. So what you do is you cut a piece of your artery or something from your leg, and then if you have a pathway that's blocked, so let's say you have a pathway that's blocked. Well, how is it blocked? What is this stuff that causes the block? It is LDL cholesterol, of course, low density lipoprotein, and this LDL stuff clogs your arteries, and now your blood can't flow through. Oh no. So what do you do? Well, you can cut a piece of artery from your leg, and then let's see, small eraser, and then you have a little hole here and a hole there, and then you attach that extra piece of artery so that it creates a new pathway, like so. Notice how we're creating a parallel pathway in your artery system, so that instead of the blood trying to squeeze in through this plaque and this this blockage, it can now flow through this new pathway. Whoa, we've increased the flow of blood. Whoa. But if you try to do that in a circuit, it might be dangerous because this new pathway has literally zero resistance, and typically current will take the path of least resistance, and it takes it in proportions, meaning the path that has more resistance will get less current, the path that has least resistance will get more current, but if a path has zero resistance, it'll get 100% current, and nothing goes through the other two. So this is called a short circuit. Short circuit. And so when the current goes, all of it will go through here, and nothing will go through here. So if these were light bulbs, these light bulbs will not work because no current will go through. And that's not because the short circuit is in front. Remember, there is no front. Even if I had drawn it this way, and I make a short circuit here, whoops, like so, okay? All of the current, if I do my current flow diagram, all of the current will come out of the battery, go straight through the short circuit, and then come out this way. This means that these two light bulbs would, or heaters or resistors, would get no power, no energy. They'd be off. They'll be cold. All right. So short circuits are bad. So what do you do if you have, to protect yourself from short circuits? Well, what you do is you put a fuse there. Now we have a fuse. Okay. This way, if this develops, so imagine a piece of hair kind of falls and it connects these circuits here somehow, making a bridge, allowing the current to flow through. So in the event that there is a short circuit that develops, this fuse will sacrifice itself because as soon as the current kind of goes up, remember, current is dependent on the resistance, and when you have zero resistance, you have infinite current. So when you're trying to pull in infinite current, that fuse would instantly melt and then just turn off the circuit for us. All right. Combo. Okay. Not all circuits are just series and parallel. You could have both. ¿Por qué no los dos? Here's a simple circuit. I'd say simple, but no, this is R1, R2, R3. This is V. Okay. Now, whether I draw R1 here at the positive end or at the negative end doesn't really matter. They're interchangeable in that I can also draw this this way. Okay. This could be R1. This could be R2. This could be R3. Okay, so it doesn't really matter. Or I can even swap the R2 and R3. It functions the same way. In all events, okay, what we want to do is simplify. Oops, let me do stroke. We want to simplify the circuit. Okay, reducing fractions. So instead of drawing these two, what we could do is first identify which resistors are in series and which ones are in parallel. Notice how at this junction, when the current goes through, always draw your current flow diagram. It's going to have to go through R1, and then it will split up into two parts, R2 and R3, and then it will recombine and go back into the battery. Okay, and so because of the splitting and recombining, we can say that R2 and 3 are parallel. R2 is parallel to R3. Okay. Now this is rec for 2. So this would be equal to product over sum, R2 times R3 over R2 plus R3. Okay. By combining R2 and 3, we've reduced this circuit. So instead of being a circuit with 3 resistors, we can actually replace R2 and 3 with the combination of 2 and 3. R1, well, I should use orange. This is R23, whatever the value is. And by combining 2 and 3, you can now see that this reduced circuit is just a circuit in series. Okay, meaning R1. Oops. Whoa. R1 is in series with R23. 2, 3 being the combination of 2 and 3. So now we can reduce it even further. Draw a battery. We just have one single resistor. And what is the value of this resistor? Well, it would be R123. And R123 in this circuit is R1 plus R2 parallel R3. All right. So if I let all the resistors be equal, so let's let R1 equal R2 equal R3 equal just the variable R, what is Req? Well, based on our equation, it's just R1 plus the parallel of R23. So this would be R plus the product over sum, R times R over R plus R. This gives us R plus R squared over 2R. This is R plus R squared over 2R. One of the R's cancel. This gives us R over 2, which is 1 plus a half is 1 1/2, or 3 halves. Okay. All right. Now that's the equivalent resistance. Once we know the equivalent resistance, we can do the total current. I total must be equal to V over Req, V tot over Req. V tot is V, and Req is 3/2 R. So this gives us 2/3 V over R. So that is what the current is. That means that this current comes out of the battery. So I total comes out, which means I total also goes in. All of it goes through. Notice how the current never splits up here. All of it goes through resistor 1. So more analysis. I1 must be equal to I total. Why is it equal to? Well, again, based on our original circuit, as soon as the current comes out of the battery, all of it has to go through resistor 1. Okay. However, it starts to split up when it hits this junction here. So some of it will go through resistor 2, some of it will go through resistor 3. But because they are equal in resistance, we said R1 equals R2 equals R3, 50% will go through each branch. So I total over 2 will go through here. And the other half goes through the other branch. So let's go and write I2 equals I3 equals I total over 2. All right. Now, what if they were different resistors? What if R2 and 3 were different? Then the current will split up proportionally. The bigger one will get less, the smaller one will get more. For this type of problem, there is the current splitter rule. Current split rule. Or current splitter rule. Okay, and you can derive this. So imagine current coming in, I, into a junction, and then it splits into two pieces based on the resistor in each branch. I'm just drawing a partial circuit here. Let's call this R1 and R2. So this is the general formula for the current split rule, in that whatever I total comes in, whatever I comes in, the splitting will happen proportionally, meaning the current that goes through resistor 1, I1, so I1 going through resistor 1, and I2 going through resistor 2. I1 is equal to the opposite resistor, R2, over the sum of the two resistors in parallel. Remember, this is only for parallel resistors. Parallel resistors. I should say two parallel resistors. Two parallel resistors. R2, the opposite resistor, over the sum of the two resistors, R1 plus R2, times the total current, I. Okay. I2, therefore, is equal to the opposite resistor, R1, over the sum of the resistors, R1 plus R2, times the total current, I. Okay, so this is the current splitter rule. You would do this, if your values in your parallel system are different. If they're the same, remember, it's going to be 50-50. You just cut it in half. Okay, but also look for patterns. Look for ratios. If it's a 2-to-1 ratio, then the current will be 1-to-2. It's a 2/3, 1/3 split. Meaning, let me give you an example. If we have, let's just say we had 100 ohms here and a 50 ohm here, okay, and only assuming that only 1 amp of current comes in, so I is equal to 1. So how much goes through here and how much goes through there? Well, it's going to be a 2/3, 1/3 split because it's a 2-to-1 ratio. If you have double the resistance, you're going to get 1/2 the current of the other one. Or just do it using our current splitter rule. So I1, which is the 100, it would be equal to the opposite resistor, 50 over 100 plus 50, times the total current, 1, which is 50 over 150 times 1, okay, which is 1/3. So this gets 1/3 of an amp going down. And if I did the other one, I don't have to if you can guess, but if you do, it would be 100 over 150 times 1, which is 2/3. So it's a 1/3, 2/3 split. 2/3 amps goes through the 50 ohm resistor. Okay. Remember, one of the rules is called Kirchhoff's junction rule, and it's that whatever goes into our dot here, our junction, has to be equal to what comes out of the junction. Again, we're going to go over Kirchhoff's rules next time, not today. Today's not. We're not going to focus on that today. All right. Now, finally, let's take a look at the voltage drops that happen in this combination circuit. Right. Let's go and use numbers now. We said that all the R's are the same. Let's go and give you some values. So 10 volts, I guess. And let's just make it 10 ohms. 10 ohms, 10 ohms. This is a squiggly. 10 ohms. Okay, so they're all 10, 10, 10. Oh, should we do one with different? Let's do one that's different. Let's do 5. No, let's keep it at 10. Alright, so we know that the same current goes through here, but it's half of the original, and the total goes through there. So let's see. Rec is equal to R1 plus the parallel of R2 and 3. This gives me 5, and 5 plus 10 is 15. Okay, so how did I do that? Well, it's this one that is in series plus the parallel of the other two. The parallel of 10 and 10 is 5. So this is 5. And so 10 plus 5 is 15. Alright, so rec is 15. The total current must be total voltage over rec, so that's 10 over 15. So that gives us 2/3 amps, which is 0.667 amps. Let's go ahead and use 3 sig figs. Yeah, I could make all of these numbers 3 if I wanted to, 10.0 or something. Anyway, since all the current, since I1 is equal to I2, since all the current goes through resistor 1, that would mean that I1 is also 0.667. Okay, so let's make a chart. I1, I2, I3, V1, V2, V3. So this is 0.667. Okay, and since resistor 2 and 3 are parallel and they're both the same, half and half will go through each. So this would be the 0.333, 0.333 amps. Okay. V1, if I wanted to look for the voltage drop at resistor 1, V1 should be V equals IR, so I1 times R1, which is 0.667 times the resistor 1, which is 10. 6.67 volts. V2 and V3 are equal. Why are they equal? Can someone tell me why they're equal? They're parallel. They're parallel. So parallel will give you equal voltages. And V2 should equal I2 R2, and that's 0.333 times 10, which is 3.33 volts, like so. I total is 0.667 amp. What is V total? Well, that's the battery. That's 10. Now wait a minute. How am I getting 13 here? Or whatever this is. What is going on? Well, remember these are routes, or pathways, and the charges can only take one pathway at a time. Charges can take one path at a time. Which means that if you choose to go through resistor 2, R2, then you're already at the bottom of the battery. You're not going to go through resistor 3. So there are 2 pathways, which we call 2 loops. This is an intro to what we're going to talk about next time. But anyway, let's see, pink. There we go. Our first loop is from the battery through resistor 1, through resistor 2, and then to the bottom of the battery. Our second loop, our second pathway, is from the battery Again, both pathways require you to take resistor 1. There's no other way. But this time we'll skip over resistor 2 and go straight into resistor 3. And then we're now back into the bottom of the battery. Okay. So notice how by taking these two pathways, we're going to drop exactly 10 volts. Okay. When I go over the first one, the resistor 1, I shouldn't say first. When I go over resistor 1, we're going to lose 6.67 volts. Okay? Remember, the resistor will convert some of that electrical potential energy into heat, and so you'll lose some of your potential. All right? And whether I take resistor 2 or 3, okay, it doesn't matter. Whether I take resistor 2 or 3, I'm going to lose the rest. I'm going to lose 3.33 volts. Okay. So you choose which pathway you want to take, and any pathway that you take will have you drop the same voltage. Your battery is like the elevator. It's going to boost you up to the 10th floor, and then after the first resistor, you're going to drop 6.67 floors. You're somewhere in limbo, I guess. But after the second one, you'll be on the ground floor at 0 volts. Okay. Now, to make it easy on ourselves, we're just setting, just like setting the initial height in Pegmaga, we say that the ground is 0 height. We're setting the bottom of our battery to be 0 volts and the top to be 10 volts. Okay. It doesn't have to be that way, in that the 10 volts on the battery suggests that there's a difference in 10 volts between the top and bottom. It doesn't necessarily mean that the bottom is automatically 10. It just makes the math easier when we do that. We could make this battery plus 5 and negative 5. This is also a delta V of 10 volts. Okay, and there are many ways to do this using grounding techniques and other things, which you can learn about next year in AP Physics C. Again, we're going to choose this model because it's easier. We always set our ground to be 0 height, so we're going to set the bottom of the battery to be 0 volts. And if I look at the power, then I can compare the brightness level of each bulb. If these resistors were bulbs instead, then the power output will tell me if it's brighter or dimmer. So let's take a look at P1. And P1 would be I1, V1, like so. Yes. Well, I got a question specifically about the worksheet that we did, the activity number 1, where I told you can use, why did you take away Streamlabs? I didn't. Wait, what do you mean? I do have Streamlabs. It still works. I don't know what you're talking about, but Streamlabs is still there. It's not on your profile. Ah, you mean I took away the link thing. I mean, it's still there. It's streamlabs.com/zphysics20. Oh, yeah. Well, I'm not a gamer streamer yet. So once I start streaming games and stuff, maybe I'll put that back on. But I mean, the site is still there technically because that's part of Streamlabs. So it's streamlabs.com/ the Twitch name. But in any case, you don't need to do that. All right. Anyway, a question was asked. Why can't I use the other power equations? Because it's giving me different numbers. And I did write in the description. So if you read the description in the YouTube video, you'll see. But basically, you should be able to use all power equations because all power equations are derived from each other and they're all the same. The reason why it wasn't giving you exactly the same number is because of number of sig figs. The ammeter was only giving you a 1 sig number, which is like 0.09 or something like that. But in reality, there's more decimal points. It's like 0.085, blah, 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 blah. And so if you use more sig figs, you'll see that you get closer and closer. Not only that, if you up your voltage, the discrepancies will be lessened. So instead of using 3 volts for a battery, if you use 30 or 300, the differences between each power function will be negligible. Right, so long story short, use any power equation. I1 V1, this will give us, let's see, I1 is 6 point, nope, let me try again. I1 is 0.667 amps, and V1 is 6.67 volts. Essentially, this is 2/3 times 10/3, right? 2/3 times 10/3 is equal to 20/9, like that. And what is 20/9? 2.222 watts. The unit for power is watts. So the first bulb that gets all of the current at the start, again, there's no start or end. We're just saying it's a start because we drew the current flow diagram that way. Gets 2.222 watts. P2 would be I2 V2, and that would be 0.333 times 3.33 volts. Okay, so that's 1/3 times 10/3. No, wait a minute. Wait a minute. 6. Oh, did I do this right? Can someone? 6.67 is 20/3. Very good. That's what I. I didn't do this right. Wait a minute. 6.67 is 20/3. So 20, that's 40. There we go. 40 over 9. 40 over 9. Thank you very much. That's twice as much. So 4.44. This one is 10/3. There we go. Because I was writing 10/3 twice. I was like, wait, both of these can't be 10/3. Yeah. Well, it's 4.444. I'm going to leave it at 44 because the 4 doesn't round up. I guess you're using 6.67, so yeah, it makes sense. This one is 1/3 and 10/3. This one is definitely right, so this would be 10/9. So that is 1.1111. I think that's how it works. Let's see, 10 divided by 9. 1.111. Okay, watts. Okay, comparison. Well, looks like the two in parallel, remember I2 and V2 are the same, so P2 is equal to P3. It's 4 times more. Means it's 4 times brighter. 4 times brighter. Alright, let's simulate this. Let's make sense of all this. Let's go back to our DC circuit kit. FET. Physics. Go to circuits. Circuit DC kit. Let's see if this actually works. We want a battery. That is 10 volts. Not 9, but 10. Okay. We want 3 light bulbs. 1, 2. How do I turn this? Let's see. Nope. Oh, I can't turn it. Whoa. Aw. Well. Oh no, go the other way. There we go. Okay, I'm just turning it so it's easier to connect. So I'm connecting our battery to our light bulb, and then this side goes into. Now this has to be a parallel system. So how do I make 2 light bulbs in parallel? Well, the bottoms of the batteries have to touch and the sides of the batteries have to touch. So this connection goes to the bottom. This connection also goes to the bottom. And the sides of the battery, sides of the light bulb have to touch. All right. And then let's see if this works. Boom. Yay. We want conventional flow, no electron flow. There we go. Okay, and as you can see, the one that is in series with the battery is getting the total current. Therefore, it is definitely brighter. Right. The quickest way to compare brightness or power values is just to look at what I you're getting. Okay. Notice how I is twice as much. We're getting 0.66 versus 0.33, and power. This is where the other power equations come in handy. Power is I squared R. And the R for each resistor is the same, 10, 10, 10. So the only thing that is different is I squared. So if you have twice as much current, you're going to get 4 times the amount of power. 4 times brighter. All right. So I think we should end it there. We will talk about some loop rules just a tiny bit. Again, we're going to start chopping some of our Unit 8 off because less of it will be tested upon this year, which means that technically our final does go up to Unit 8, but less of it will be on Unit 8, more of it will be on the other units. And we're still preparing for our AP test because it's not canceled. But we're going to go from Unit 1 through 7.5 for the AP test, which covers up to simple harmonic motion, shim. No sound waves though, so I don't think sound is going to be on it. But in any event, you guys know everything, so I'm going to compare you to all other students who have come before you, not just people here this year. But we've gone through our program just like as if the schedule was the original schedule, so all the units were mapped out based on that schedule. So we're technically done. We are ahead of most schools that are not on Unit 8. Next stream will be Monday. Yeah, it's weekend time. Time to stream some video games? I don't know. What games are you going to stream? I don't know. What games are actually fun? I'm not sure. But anyway, let me close this stream, and then after the stream, I can open it up for a few more minutes for some Q&A time. Thank you for tuning in. I'll see you next time.